Hello and welcome to Random Topics with Jack, the podcast where we explore the intriguing and sometimes controversial topics that shape our understanding of the world. Last time we rolled the dice and took a retrospective journey through the world of Dungeons and Dragons. We explored its roots in wargaming, the contributions of Gary Gygax and Dave Arneson, its evolution to different editions, and how it went from a niche tabletop game to a cultural phenomenon influencing video games, streaming, storytelling, and modern geek culture. It was quite the adventure, and I hope you all enjoyed looking at how a game built around imagination, collaboration, and a few suspiciously pointy dice managed to captivate millions of people across decades. And speaking of things that started as niche interests and then suddenly became impossible to avoid, today we're looking at a topic that has gone from science fiction to everyday life at a frankly ridiculous speed: artificial intelligence. AI is everywhere at the moment. It's helping people write emails, generate artwork, summarize documents, edit images, create music, write code, search through information, and even assist scientists in areas like medicine and biology. Now, depending on who you ask, AI is either the greatest tool humanity has ever created since the internet, or is the beginning of the end and we should all start being polite to our toaster just in case. As usual, I imagine the truth is somewhere in the middle. Because AI is not magic, it is not one single thing, and despite what some headlines might suggest, it's not a tiny digital brain sitting in a data center plotting how to steal your job and write mediocre LinkedIn reviews. Although, to be fair, it's already pretty good at LinkedIn posts. But in this episode, we are going to take a beginner-friendly journey through what AI actually is, how it works, and why it's become such a huge part of modern technology today. We'll look at the difference between AI, machine learning, neural networks, and generative AI. We'll talk about large language models, also known as LLMs, which are the tools behind the likes of ChatGPT, Claude, Gemini, and Grok. We'll explore how these models use tokens, context, and prediction to generate responses that can feel surprisingly human. And we'll also look at how AI systems are trained, including pre-training, fine-tuning, and human feedback. We'll also step away from the abstract side of AI and look at the very real infrastructure behind it: data centers, GPUs, electricity, cooling, and the physical cost of keeping the cloud running. And finally, we'll look at the AI industry itself, because AI is not just one company or one tool, it's a whole ecosystem of organizations building different systems for text, images, music, video, voice coding, research, and much more. The aim today is not to turn you into an AI engineer, thankfully, because if that was the goal, we'd need a much longer episode and probably a stronger coffee. But the aim is to give you a clear mental map. By the end of this episode, you should be able to hear terms like LLM, Gen AI, machine learning, tokens, training data, data centers, and have a solid understanding of what they mean and how they connect. Because once we understand what AI is and how it works, we can have much better conversations about its benefits, its risks, and its ethical implications. And that's going to be the focus of the next episode. But today, we're starting at the beginning. How did we teach machines to recognize patterns, make predictions, and create outputs that look, sound, and sometimes feel intelligent? Let's get started. Artificial intelligence. It's one of those phrases that's become almost impossible to avoid over the last few years. Whether it's writing emails, generating artwork, helping scientists discover new medicines, or simply answering questions like the one you're listening to now, AI seems to be everywhere. Depending on who you ask, it's either the greatest technological breakthrough since the internet or the beginning of the end of civilization. As is often the case, the truth probably lies in the middle. But before we understand what AI is, we need to answer a different question. Why did we want to build it in the first place? Human history is in many ways a story of solving problems. When lifting heavy objects became difficult, we invented levers and pulleys. When travelling long distances took too long, we built ships, trains, and airplanes. When calculations became too complex to do by hand, we created computers. Each invention wasn't about replacing people, It was about extending what people were capable of. Artificial intelligence is simply the latest chapter in that story. For decades, scientists, mathematicians, and computer engineers have been asking a fascinating question. Can we build a machine that doesn't just calculate, but can also recognize patterns, make decisions, and help solve problems? Notice I didn't say think, and that's an important distinction we'll come back to later. Because despite what films, TV, and sci fi might have us believe, the AI we use today isn't sitting there wondering about the meaning of life or plotting world domination. It's doing something both less dramatic and in many ways far more interesting. It's recognizing patterns. If you ever recognized your friend's face in a crowd, finished the lyrics to a song you've heard 100 times, predicted how a sentence was going to end before someone finishes speaking, or instinctively known that dark clouds probably mean rain is on the way, you've used one of the most powerful abilities the human brain possesses: pattern recognition. Modern AI is, at its heart, an attempt to teach computers to recognize patterns too. And sometimes those patterns are words, sometimes they're images, sometimes they're sounds, videos, or even the structures of proteins living inside organisms. The underlying idea, however, is remarkably similar. Teach a computer to recognize enough patterns, and eventually it can begin to make useful predictions. And as we'll discover throughout this episode, prediction turns out to be surprisingly a powerful idea. So now we know why AI exists, the next question almost asks itself: what actually is artificial intelligence? Well, here's where things get a little more complicated than the headlines might suggest. When people hear the term artificial intelligence, they often imagine a machine that's thinking the same way humans do, a digital brain that's self-aware, conscious, and capable of independent thought. And the reality is much less like science fiction. Artificial intelligence is really an umbrella term, rather than describing one specific technology. It refers to a whole family of technologies designed to perform tasks that normally require human intelligence. Those tasks might include recognizing faces in photographs, translating between languages, recommending films you might enjoy, spotting fraudulent bank transactions, or even helping doctors identify diseases from medical scans. The important thing to remember is that these systems aren't all built the same way. In fact, when people say AI, they could be referring to several very different technologies. That's one of the reasons conversations about AI can become confusing so quickly. Two people might both be talking about AI while actually describing completely different kinds of systems. Take a calculator as an example. A calculator follows a fixed set of rules. Ask it what 2 plus 2 is today, tomorrow, or 10 years from now. The answer will always be 4. It doesn't learn, it doesn't adapt, it simply follows instructions. Many early computer programs worked exactly like that. Every possible decision had to be programmed by a human beforehand. Modern AI is different. Instead of being told every rule explicitly, many AI systems learn patterns from data. Rather than being programmed to recognize every single breed of dog by hand, for example, an AI system might be shown thousands, even millions, of labeled images until it begins recognizing the patterns for itself. That shift from following instructions to learning patterns is one of the biggest milestones in the history of computing. It's also why you'll hear people use another term alongside artificial intelligence: machine learning. And we'll come back to that in a moment because it's one of the most important ideas to understand. But before we do, though, there's one misconception worth clearing up. AI isn't intelligent in the way people are. It doesn't have beliefs, emotions, ambitions, or consciousness. It doesn't get excited when it solves a difficult problem. It also doesn't get frustrated when it makes a mistake. What it does have is an extraordinary ability to detect patterns that would be impossible for most humans to find simply because of the sheer amount of data involved. And that's why AI can sometimes appear incredibly intelligent. When an AI writes a poem, generates a picture, or answers a question, it can feel as though it's thinking. What's actually happening is something quite different. It's making an astonishingly sophisticated prediction based on everything it learned during training. Sometimes these predictions are incredibly useful. Sometimes they're wrong. And sometimes they're so convincing, it's difficult to tell the difference. And we'll explore why that happens in our next episode when we talk about AI hallucinations. But for now, there's one important takeaway that I'd like you to remember. Artificial intelligence isn't one machine. It isn't one company. It isn't even one technology. It's a collection of different approaches to solving problems that have one thing in common: teaching computers to perform tasks that once only humans could do. So now we know what AI is. The next question becomes, how does a computer actually learn to recognize these patterns in the first place? So I think it's helpful to think of AI a bit like a family tree. At the very top sits artificial intelligence itself. That's the broadest category covering any computer system designed to perform tasks we'd normally associate with human intelligence. As researchers explored different ways of achieving that goal, several different branches began to emerge. One of the largest, by far the most influential today, is called machine learning. Machine learning is exactly what it sounds like. Rather than giving a computer a fixed list of instructions to follow, we allow it to learn patterns from examples. Imagine you're trying to teach a child what a cat looks like. You probably wouldn't give them a list of measurements describing the average length of a cat's tail, the exact angle of its ears, or the number of whiskers it should have. Instead, you'd show them lots of cats. Eventually, they begin recognizing the pattern for themselves. Machine learning works much in the same way. Instead of programming every possible rule, we train a model using large amounts of data until it begins identifying patterns we want it to recognize. As computers become more powerful and researchers develop new techniques, another branch grew out of machine learning, and this is known as deep learning. Now, don't let the name intimidate you. The deep doesn't mean it's especially complicated or mysterious. It simply refers to the number of layers inside a particular kind of system known as a neural network. Neural networks are very loosely inspired by the way neurons in the human brain connect together. And I want to stress the words very loosely here. They don't think like brains, and neuroscientists certainly wouldn't mistake one for the other. The idea is simply that information passes through multiple layers, with each layer recognizing increasingly complex patterns. To use image recognition as an example, the first layer might notice things that are simple, like edges and lines. The next will begin recognizing shapes, and further layers might identify eyes, noses, or ears. Eventually, after passing through enough layers, the system has enough information to conclude it's probably looking at a cat. Those deeper neural networks are what we call deep learning. They're responsible for many of the AI breakthroughs we've seen over the last decade. But that's still not the whole family tree. Another fascinating branch is reinforcement learning. Rather than learning from examples, reinforcement learning learns through trial and error. Imagine teaching a dog a new trick. When it does something you want, you reward it with a treat. Over time, it begins repeating behaviors that earn rewards and avoiding behaviors that don't. A reinforcement learning system works in a surprisingly similar way. It performs an action, receives feedback, and gradually learns which decisions lead to the best outcomes. This approach has been used to train AI systems that can master board games, control robots, and even help optimize complex industrial processes. But there's also a smaller but incredibly interesting branch known as evolutionary AI. Instead of learning through examples or rewards, these systems borrow ideas from evolution itself. Thousands, sometimes millions of possible solutions are created. The best performing ones are kept, the weaker ones discarded. Over many generations, the solution gradually improves, rather like natural selection in biology. If you've ever watched Code Bullet on YouTube, you've probably seen this in action. He often experiments with techniques like NEAT, which stands for Neuroevolution of Augmenting Topologies. Watching virtual creatures gradually learn to walk, drive, or play games is a brilliant way to see evolutionary algorithms at work. And finally, we arrive at the branch that's captured the world's attention over the last few years: generative AI. Unlike many earlier AI systems that focused on recognizing patterns and making decisions, generative AI does something different. It creates. It can write stories, generate images, compose music, produce videos, write computer code, and much more. But here's the clever part. It isn't creating those things out of thin air. It's using exactly the same fundamental idea we've been talking about throughout this episode: pattern recognition. It has learned so many patterns from its training that it can begin predicting entirely new combinations that have never existed before. And that brings us to the question that has probably been sitting quietly in the back of your mind since the start of this episode. How can a computer possibly learn enough patterns to write an essay, generate a picture, or hold a conversation? Well, to answer that, we need to take a closer look at generative AI itself. So, what exactly makes generative AI different? Well, the clue's in the name. Most traditional AI systems are designed to recognize something or make a decision. Is this email spam? Does this X-ray show signs of disease? Should this bank transaction be flagged as suspicious? Generative AI takes things one step further. Instead of simply analyzing information, it creates something new based on everything it's learned. That something might be a paragraph of text, a painting, a song, a video, even computer code. Now, I know what some of you might be thinking. If it's creating something new, where's it getting its ideas from? And that's one of the biggest misconceptions surrounding generative AI. It doesn't have imagination in the human sense. It doesn't sit there waiting for inspiration to strike. Instead, it's making incredibly sophisticated predictions based on patterns it learned during training. Take language as an example. Imagine I started a sentence by saying fish. There's a very good chance your brain immediately filled in the next word or two. You might have thought and chips, maybe seafood, maybe even fingers. Whatever you came up with, you weren't searching through every sentence you've ever heard. Your brain simply recognized which words commonly follow another one. Modern language models do something surprisingly similar. Instead of drawing on years of personal experience, they've learned statistical patterns from unimaginably large amounts of text. Every word, or more accurately, every token, we'll come back to exactly what a token is shortly, is another prediction. One prediction leads to the next, then the next, then the next again. Eventually, those tiny predictions build into complete sentences, paragraphs, and conversations. The same principle applies to images. An image generator doesn't have a little hidden artist inside the computer carefully painting each picture. Instead, it's learned patterns relating to colour, shape, lighting, texture, perspective, and countless other visual features. When you ask it to generate, say, a Highland cow wearing a spacesuit standing on Mars, it isn't searching for an existing image that matches your request. It's predicting what those visual patterns should look like when combined in a way that's consistent with everything it's learned during training. Music generators learn patterns in rhythm, harmony, and melody. Video generators learn patterns in movement, lighting, and motion from one frame to the next. Different media? Same underlying principle. Pattern recognition leading to prediction. And by now, you have noticed something interesting, hopefully. Whether we're talking about text, images, music, or video, everything seems to come back to the two same ideas we've mentioned throughout this episode: learning patterns and making predictions. So if prediction is doing all the heavy lifting, how does a language model actually decide what the next word should be? So far, we've built up a picture of artificial intelligence as something that learns patterns and uses those patterns to make predictions. And that brings us to one of the most important questions in this episode. When you type a question into an AI like ChatGPT, what is it actually doing? Well, let's start with the simplest possible version of the answer. It's predicting text. That might sound almost too simple to be true, but it's the core idea behind a large language model. A large language model, or LLM, is an AI system trained to predict the next piece of text in a sequence, not the next idea, not the next answer, just the next small chunk of text. And these small chunks are called tokens. A token can be a word, part of a word, or sometimes even just punctuation. The important thing isn't the exact definition, but the idea that language is broken down into small pieces and the model is constantly predicting what comes next. So, back to our original example, if I wrote fish, the model is essentially asking itself, what is the most likely thing to come next based on everything I've seen before? And it might, predict the things that we've already said, and chips or fingers, but it could also go tank, species, supper. Each option has a probability attached to it. Not because the AI knows what fish are in a human sense, but because it's seen billions of examples of how language is used. And then it picks one, and then it does it again, and again, and again. One token at a time, building up a full response step by step. That's why conversations with AI feel so natural. It isn't planning out a full paragraph in advance like a human might when writing an essay. It's generating the response in real time, constantly predicting the most likely next step in the sentence. Now, if you've ever used one of these systems, you might have noticed something interesting. Sometimes it's incredibly accurate. Sometimes it's confidently wrong. And sometimes it produces something that sounds completely believable, even when it's not actually true. This is where things get important, because the model isn't checking facts. It's not searching a database. It's not verifying information against reality. It is, quite literally, continuing a pattern. That's why it can sometimes produce what people call hallucinations. Responses that sound right, but aren't actually correct. Not because it's trying to mislead you, but because the only thing it knows how to do is predict what text usually comes next. Now, you might be wondering, if it's just predicting text, how does it seem to understand my question at all? And the answer lies in something called context. When you send a message to an LLM, it doesn't just see your last sentence, it sees the whole conversation up to that point. Every message you've sent, every reply it has given, all of that gets processed together, and the model uses it to make better predictions about what should come next. So when you have a back and forth conversation with an AI, what you're really doing is continually updating the context it uses to predict the next token. It feels like memory, it feels like understanding, but what's actually happening is a pattern matching at an incredibly large scale. Now, there's one more piece to the puzzle we need to introduce before this all fully makes sense, because so far we've talked about what it does, but not how it learned to do it in the first place. And that takes us into something called training. Now, when we say an AI model is trained, we don't mean someone sat down in front of the computer with a notebook and a wee cup of tea, although honestly, if that worked, I'd respect the commitment. Training an AI model means exposing it to enormous amounts of data and adjusting the model over and over again until its predictions become better. For a language model, that might include books, websites, articles, code, essays, conversations, documentation, and any other forms of written text. The goal isn't for the model to memorize every single thing it reads, and that's the important distinction. It's not supposed to become a giant filing cabinet of copied sentences. Instead, it learns patterns. Patterns in grammar, patterns in facts, patterns in reasoning, patterns in style, patterns in how questions are usually answered, patterns in how code is written, patterns in how humans explain things to each other. The first major stage of this is usually called pre-training. That's the P in GPT, Generative Pre-trained Transformer. And GPT is the model family most people know through ChatGPT, even though tools like Claude, Gemini, Grok, Suno, and many others use different model families or techniques. But during pre-training, the model is given a huge amount of text and asked to do a deceptively simple task: predict the missing piece. For example, it might see a sentence like "the capital of France is," and at the beginning of its training, its guesses are basically nonsense. It might guess banana, it might guess running, it might guess something that makes absolutely no sense at all. But each time it guesses, the training system compares its prediction with the correct answer and adjusts the model slightly. Not dramatically, slightly. And then it does it again, and again, and again. Millions, billions, even trillions of times. Over time, the model becomes better at predicting what comes next. And because language contains so much information about the world, getting better at predicting language also means the model begins to pick up all sorts of other patterns. It learns that Paris is associated with France, that Shakespeare wrote plays, that Python can be both a snake and a programming language, that "I'm sorry to hear that" is more likely to follow bad news than congratulations. It learns that these relationships, not because someone programmed each one by hand, but because those patterns appear again and again throughout the data. This is one of the strangest and most powerful things about modern AI. By learning to predict language, it starts developing abilities that look like understanding. But pre-training alone isn't enough. A raw pre-trained model might be good at continuing text, but that doesn't automatically mean it's good at being helpful. If you asked it a question, it might continue in the style of a textbook, or a forum argument, or a customer service email, or a Reddit comment from someone who should probably go outside more often. So after pre-training comes another stage, fine-tuning. Fine-tuning is where the model is trained on more carefully selected examples. Instead of learning how language works in general, it starts learning to behave as an assistant, how to answer questions clearly, how to follow instructions, how to summarize information, how to explain technical subjects, how to say, I don't know, instead of just making something up. At least that's the goal. Fine-tuning is a bit like taking someone who has read an entire library and then teaching them how to be useful in a conversation. They already know a lot of patterns. Now you're teaching them how to apply those patterns in a useful way. There's also another important stage called reinforcement learning from human feedback, often shortened to RLHF. It sounds very technical, but the idea is actually fairly intuitive. Humans look at different responses from the model and rank which ones are better. For example, suppose the user asks explain black holes to a beginner. One answer might be technically accurate, but filled with dense academic language. The other might use a simple analogy, explain the basics clearly, and avoid unnecessary jargon. Most humans would probably prefer the second one. So that feedback helps train the model towards responses that people find more useful, more clear, and more appropriate. It's not just about being correct, it's also about being understandable. And that matters a lot, especially because a technically correct answer that nobody can understand isn't very helpful. And this is also where safety training comes in. Models are shown a lot of examples of requests they should answer, requests they should refuse, and requests where they should redirect towards safer information. So if someone asks how nuclear fission works at a high level, the model can explain the science. But if someone asks for instructions on how to build a nuclear weapon in their garden, the model should refuse. And that doesn't happen because it has a single banned phrase hidden inside a list. It happens because the model and the systems around it have been trained to recognize categories of potentially harmful requests and respond appropriately. And even then, the safeguards aren't perfect. They're constantly tested, updated, and improved because any powerful tool can be misused. We'll talk much more about that in the next episode when we get into the ethical implications of AI, though. But for now, the important thing is training has multiple stages. First, the model learns broad patterns and enormous data sets. Then it's refined to be more useful. Then human feedback helps guide it towards responses that people actually want. And then finally, additional safety systems try to reduce harmful or dangerous behaviour. And that's how we can get from a model that can simply continue text to something that feels like it can answer questions, explain concepts, write code, brainstorm ideas, and hold a conversation. But all of this comes with a cost, because training and running these models require an enormous amount of computing power. And computing power doesn't come from nowhere. It needs chips, it needs electricity, it needs cooling, it needs physical buildings filled with servers, which means to understand modern AI properly, we need to leave the abstract world of models and predictions for a moment and visit the very real buildings where the cloud actually lives. Data centers. So far, we've talked about AI as something abstract, models, tokens, trainings, predictions, patterns, but AI doesn't live in some magical digital mist. It lives somewhere very real. In buildings. Huge buildings. Filled with servers, networking equipment, cooling systems, backup power, batteries, cables, security systems, and more blinking lights than a Christmas display designed by a network engineer. These buildings are called data centers. And if you've ever heard someone say something is stored in the cloud, this is what they actually mean. The cloud is not a fluffy little server floating gently above us, no matter how much the tech marketing would like us to imagine that. The cloud is someone else's computer. Or more accurately, thousands upon thousands of computers sitting inside highly specialized buildings around the world. When you stream a film, save a file to Google Drive, scroll through social media, send an email, or use online banking, or even ask AI a question, that request usually travels across the internet to a data server somewhere. The data center processes it, stores it, retrieves it, or sends something back. In normal everyday computing, data centers already do an enormous amount of work, but AI has changed the scale of that demand. A traditional data center might run websites, databases, apps, email systems, and cloud storage. An AI-focused data center has a much more intense job. It needs to train and run massive neural networks, and for that, it needs serious computing power. This is where we need to talk about GPUs. A GPU is a graphics processing unit. Originally, GPUs became famous because of gaming. They're the chips responsible for rendering graphics, lighting, shadows, textures, and all the visual chaos happening on your screen when your game decides to melt your PC. But it turns out, GPUs are also incredibly good at the kind of maths AI needs. AI training involves huge numbers of calculations happening at the same time, especially something called matrix multiplication. And don't worry, we're not going down a maths rabbit hole today. The important point is this. GPUs are very good at doing lots of small calculations in parallel. A normal CPU, the main processor in your computer, is brilliant at handling a wide range of general tasks. A GPU is more like an enormous team of workers all doing similar small tasks at once. And that's exactly what AI needs. A large AI model can require thousands or even tens of thousands of GPUs working together. They all need to communicate with each other at extremely high speeds, they all need electricity, they all produce heat, a lot of heat, and that heat has to go somewhere. That's why cooling is such a major part of data center design. Some data centers use huge air cooling systems. Others use liquid cooling, where coolant is moved directly around the hardware to pull heat away more efficiently. There are even systems where equipment can be submerged in a special non-conductive fluid, which all sounds ridiculous until you remember we're talking about buildings full of machines doing more maths in a few seconds than most of us will do in our entire lives. Power is the other major issue. AI data centers can require enormous amounts of electricity. Some proposed or planned facilities measure in hundreds of megawatts. To put that in perspective, a 300 megawatt data center is not just a big building with computers. That is infrastructure on the scale of a small city's electricity demand. And that's before we even talk about backup systems. Data centers cannot just casually switch off. If the power drops, services go down. Training runs can be interrupted, data can be lost or corrupted, customers get angry, companies lose money. So data centers are built with redundancy in mind. Multiple power feeds, backup generators, battery systems, failover systems. The whole idea is that if one thing fails, something else immediately takes over. This is where battery energy storage systems, or BESS, comes in, and is really quite interesting. A large battery can store electricity and release it when needed. For a data center, that can help smooth demand, provide backup power, and support the wider electricity grid. So, in places with lots of renewable energy, like here in Scotland, that becomes especially relevant. Renewables are fantastic, but they're also variable. Wind output changes, solar output rises and falls with daylight and weather. Hydro can provide more stability, but the overall grid has to balance supply and demand moment by moment. A large battery system can store excess electricity when generation is high and release it when demand rises or generation drops. So a data center compared with a large BESS isn't just a building that consumes power. It can become part of the wider energy infrastructure. Now, that doesn't mean data centers are automatically good for the environment. Absolutely not. They use a lot of electricity, they need land, they produce heat, they require cooling, they can create noise, and they can put pressure on local infrastructure. In countries where electricity is still very reliant on fossil fuels, increased data center demand can mean more carbon emissions. But the picture's not the same everywhere. A data center powered by coal-heavy electricity is a very different environmental footprint from one operating in a region with lots of wind, hydro, solar, or low carbon energy sources. And this is why location matters. It's also why the conversation around AI infrastructure needs nuance. Saying AI data centers are bad is too simple. Saying AI data centers are fine when renewables exist is also too simple. The real question is, where are they built, how are they powered, how efficient are they, what happens to the heat, how do they affect the local communities, what trade-offs are being made, because data centers are now part of the physical cost of artificial intelligence. Every AI-generated image, every chatbot response, every video model, every training run, all of it depends on real machines and real buildings using real electricity. And that's one of the most important things to remember. AI might feel weightless when you type into a chat box, but behind that response is infrastructure, servers, chips, power lines, cooling systems, land, water, energy, people maintaining it all. The cloud is physical. And as AI grows, that physical footprint grows with it. And so now that we understand what AI is, how it learns, the buildings that make it possible, there's one more piece of the puzzle to look at. And that's who's building this ecosystem. Because AI is not one tool, not one model, and it's not one company. It's an entire industry. Because although we often talk about AI companies as if they're all doing the same thing, a lot of them are actually taking very different approaches. Some companies are trying to build entire ecosystems around AI. OpenAI is probably the clearest example of this. Most people know ChatGPT, but ChatGPT is only one part of the wider OpenAI ecosystem. They also have DALL-E for image generation, Sora for video generation, Whisper for speech recognition, voice systems, coding capabilities, and tools like Operator that move towards AI agents. In other words, OpenAI isn't just building one AI tool. They're trying to build a whole stack of AI systems that can work across text, images, audio, code, video, and actions. Google is another major ecosystem builder. Through Google DeepMind and the wider Google AI ecosystem, they have Gemini for language and multimodal AI, Imagen for images, Veo for video, and tools connected to search, productivity, science, and research. And that makes sense when you remember that Google already has search, YouTube, Android, Gmail, Google Docs, Google Cloud, and an enormous data center infrastructure. For a company like Google, AI isn't just a product, it's something that can be woven through almost everything they already do. And then you have companies like Anthropic, who are more focused around one central model family, Claude. Claude can be used for many different things: writing, coding, analysis, research, summarizing documents, and more. But Anthropic's approach is much more Claude-centered. Rather than having lots of separate branded tools for every type of media, they've focused heavily on making Claude safer, more reliable, and more useful as a general-purpose assistant. There's also more specialized companies. Midjourney is strongly associated with image generation. Runway and Pika are known for video generation. Suno and Udio are known for music generation. Elven Labs is known for voice gen. These companies aren't necessarily trying to build the entire AI universe under one roof. Instead, they're focusing on one particular area and trying to do it extremely well. And then underneath all of this, there's another hidden layer: shared models, open source models, and APIs. Some AI products you use may not be powered entirely by the company whose logo is on the website. A writing app might use another company's language model. A design app might use another company's image model. A transcription tool might use the speech model developed somewhere else entirely. So the AI industry isn't one neat stack. It's more like a giant web. You have companies building full ecosystems, companies specializing in one type of generation, companies providing infrastructure, companies building open source models, companies stitching several of those pieces together into tools aimed at ordinary users. And that's why conversations about AI can get messy quickly. When someone says AI, they might mean ChatGPT, or Claude, or Midjourney, or Suno, or a medical imaging tool, or a data center full of GPUs, or an open source model running on someone's own computer. All of those things are connected, but they're not identical. And that's probably one of the biggest takeaways from this episode. AI is not one tool, it's not one company, it's not one model, it's an ecosystem. A fast-moving, messy, powerful, controversial ecosystem built around one central idea: teaching machines to recognize patterns well enough that they can make useful predictions. And now we've looked at what AI is, how it works, how it learns, where it lives, and who's building it, we're ready to ask the harder question: what happens when we start using it everywhere? But that's a question for another day. Today, we've taken a journey through the world of artificial intelligence, from the big picture question of why humans wanted to build intelligent machines in the first place, all the way down to the physical buildings that make modern AI possible. We started looking at what AI actually is. It's not magic, it's not consciousness, not a tiny digital person living inside your laptop. Sadly, if there was one, I'd hope he'd at least help clear my desktop. Instead, we saw that AI is a broad family of technologies designed to perform tasks that normally require human intelligence. From there, we explored the AI family tree: machine learning, where systems learn patterns from data; deep learning and neural networks, where information passes through layers that recognize increasingly complex patterns; reinforcement learning, where systems learn through trial and error; evolutionary AI, where solutions improve over generations in a way inspired by natural selection. Then we arrived at the branch that's captured so much attention over the last few years: generative AI. We looked at how Gen AI creates text, images, music, video, and code, not through human-style imagination, but through pattern recognition and prediction. That took us under the hood of large language models, where we talked about tokens, contexts, prediction, and why a system like ChatGPT can feel like it understands us, even though what it's really doing is predicting the next piece of text based on patterns it has learned. We also looked at training, like pre-training, where the model learns broad patterns from huge datasets; fine-tuning, where it becomes more useful and more assistant-like; human feedback, where responses are shaped towards being clearer, safer, and more helpful; and safeguards, where systems are trained to refuse harmful requests while still allowing useful education and discussion. We then pulled back the curtain on the cloud and found something much less fluffy: data centers, real buildings, real servers, real GPUs, real electricity, real cooling systems. Because AI may feel weightless when we use it, but the infrastructure behind it is very real. Finally, we looked at the AI industry itself. Some companies like OpenAI and Google are building large ecosystems across text, images, audio, video, code, and agents. Others, like Anthropic, are more focused around a central model family like Claude. Others specialize in particular areas like Midjourney for images, Runway Pika for video, Suno Udio for music, and Elven Labs for voice. So if there's one idea I want you to take away from this episode, it's this: AI is not one thing, it's not one tool, it's not one company. It's an ecosystem of technologies built around recognizing patterns, making predictions, and using those predictions to create or support useful outputs. But of course, once we understand AI, what AI is and how it works, the next question becomes much more complicated. What happens when we start using it everywhere? Because AI can be incredibly useful. It can help with research, learning, creativity, accessibility, productivity, and scientific discovery. But it also brings problems: hallucinations, copyright disputes, privacy concerns, environmental costs, deepfakes, misuse, and the very human risk of letting a tool do all of our thinking for us. So next time, we'll be taking AI out of the server room and putting it under the microscope. Or maybe the courtroom. Probably not literally. I don't have the budget for a robot witness stand. But we will be looking at the pros, the cons, and the ethical implications of artificial intelligence. Because as powerful as AI is, the real question isn't just what can it do, it's what should we let it do. Thank you for all joining me today as we explored the patterns, predictions, and physical infrastructure behind modern AI. As always, I've been your host, Jack, and until next time, keep questioning and exploring.